In my earlier video, I had discussed about vector space and subspace of a vector space. In my today's video, goal of this lecture is how I will get new subspaces from the old subspaces. This is very interesting topic. From old subspaces, I will create new type of subspaces. This is today's goal of my lecture. Then our next goal is linear combination and span of a vector space. Actual idea of span is given a set of vectors. If you apply any linear combination to the set of vectors, it's still within the vector space. This is very interesting topic. By any vector, you can generate whole space. This is the idea of span. That means today I will discuss new two topic. How I will get new subspaces from the old subspaces and linear combination and span of a vector space. And this topic is more important for not only any competitive exam, for higher study, not only vector space, metric space, topology, actually for pure mathematics. Our next goal is what is the largest subspace of V that contain in both W1 and W2. Obviously W1 intersection W2 contain in both W1 and W2. And W1 intersection W2 be the largest subspace of the vector space V, which contain in both W1 and W2. Our next goal is let V be a vector space and W1, W2 are subspaces of the vector space V. Then what is the largest subspace of the vector space V that is contained in both W1 and W2? If W1 be subspace and W2 be subspace, then their intersection obviously be subspace. And their intersection be the largest subspace which contain both W1 and W2. Let's check quickly how W1 intersection W2 be subspace of V. The theorem is consider V be vector space and W1 and W2 be subspace of V. Then their intersection always be subspace of V. Here noticeable W1 and W2 be old subspace and now I will see their intersection always be subspace of V. This is obviously true. Very easy type theorem. We have to show the vector 0 belongs to W1 intersection W2 and lambda u plus mu v belongs to W1 intersection W2. And since W1 and W2 be subspace, so obviously the vector 0 belongs to W1 and vector 0 belongs to W2. That imply vector 0 belongs to W1 intersection W2. Now consider lambda mu belongs to F means field and 2 vector uv belongs to W1 intersection W2. That imply uv belongs to W1 and uv belongs to W2. And since W1 be a subspace, then lambda u plus mu v belongs to W1. And also since W2 be subspace, then lambda u plus mu v belongs to W2. And from this expression, since this is AND, so obviously lambda u plus mu v belongs to W1 intersection W2. That means if W1 and W2 be subspace of V, then their intersection obviously be subspace of the vector space V. Consider one example, V equal to R3 and W1 be the set of those vector A, B, 0 where A, B belongs to real number. That means here the set of those vector whose z coordinate be 0. And this is actually since here the z coordinate be 0, this is actually the xy plane. And W2 be the set of those vector which contain A0, B. AB belongs to real number. This is actually here y coordinate be 0, that means this is actually xz plane. What would be the W1 intersection W2? Here W1 intersection W2 only, notice, only would be set of those vector such that A0, 0 where A belongs to real number. And in R3, set of those vector A0, 0 means only the x-axis. That means here only the line of intersection. This is, notice, this is xz plane and this is xy plane, and this is the line of intersection of this plane. Are you getting? That means largest subspace of this subspace B is line of intersection. So, if V is any vector space and W1, W2 are subspaces of the vector space V, then their intersection obviously be subspace of the vector space, and their intersection is the largest subspace that is contain both W1 and W2. Next goal, what is the union of two subspace? Is union of two subspace be subspace? As for example, consider V equal to R2 and consider U equal to set of those vector which contain A0 where A belongs to real number. That means this is the only here R2 means xy plane, this is U only this x-axis, and consider V equal to set of those elements 0B where B belongs to R. That means V be the set of y-axis, then U intersection V, obviously the 0, 0 vector, which is obviously be space. But now if we consider U union V, then is this space is subspace? Obviously, U union V means either x-axis or y-axis. Consider one vector 1, 0 belongs to union V and other vector 0, 1 belongs to U union V. Then their sum would be 1, 1, and this does not belongs to U union V. Okay? Therefore, U union V is not be a subspace of the vector space V. Actually, V be a vector space and W1, W2 be subspace of the vector space V. Then their union means W1 union W2 does not have to be subspace. And it is subspace if and only if either W1 contain W2 or W2 contain W1. That means when W1 contain W2 or W2 contain W1, then their union always will be subspace. Next goal is, what is the subspace that contains both subspace W1 and W2? Let V be a vector space and W1 and W2 are subspace of the vector space V. Then their sum W1 plus W2 is the set of those elements x plus y where x belongs to W1 and y belongs to W2. Then this is easy to verify. W1 plus W2 always be subspace of the vector space V, and This subspace means W1 plus W2 is the smallest subspace of the vector space V that contains both W1 and W2. This is the picture of W1 plus W2. Here W1, here W2, here W1 intersection W2, and this is W1 plus W2. This is actually those x plus y, where x belongs to W1 and y belongs to W2. In previous example, I have seen union V is not subspace of the vector space V. But if we consider U plus V, this is actually the set of those elements, something in U and something in the V. Then U plus V would be AB, where AB belongs to real number. And this is actually the whole R2. And obviously, whole R2 always be subspace. That means U plus V be subspace of the vector space V equal to R2. And this subspace be the smallest subspace of this vector space. Are you getting? I will discuss linear combinations and span of a vector space. I have told you few minutes ago, if we know what is the span of a vector space, then you can generate whole space by vectors. At first, let's see what is the linear combination of a vector space. A linear combination of a set of vectors v1, v2 up to vn is given by multiplying each vector by corresponding scalar coefficient in the result. And this would be alpha 1 v1, alpha 2 v2 up to alpha n vn. For example, see the vector 1, 3. This is actually the linear combination of minus 3 times the vector 1 minus 1 plus 4 times the vector 0, 2 plus 2 times the vector 2 minus 4. That means this vector 1, 3 is a linear combination of the vector 1 minus 1, 0, 2 and 2 minus 4. Actually, the general linear combination is look like, consider the vector 2, 0 minus 3 minus 1, 0, 5. This is look like C1 times 2, 0 minus 3 plus C2 times minus 1, 0, 5. That means scale the first vector. Then scale the second vector. Now add these two vectors. And this produced a new vector. This is the new vector 2c1 minus c2 0 minus 3c1 plus 5c2. If we consider the vector 5 minus 3 4, this cannot express this linear combination of these two vectors, because here at the second coordinate the term is 0, but here the second coordinate the term is minus 3. A lot of problem end up by looking like this. You have bunch of vector v1, v2, vn. Now scale them and add them. Then always you will get the new vector v. And matrix multiplication is actually such type. Suppose consider A as m cross n matrices and v as a vector from Rn. Then we can write as, here A is the m cross n matrices. Consider A1 as first column, A2 as second column up to An as nth column, and V as a vector V1, V2 up to Vn. This is the coordinate. Then matrix vector product AV is the linear combination. Such here the product is such type. V1 times A1, A1 here the vector, here the first column, 1 be the here the scalar. This is the first component of the vector V. then A2 scale by the component V2. Similarly, the vector AN scale by Vn, then add them, then I will get the new vector AV. Okay. As for example, consider the matrix is 2 cross 3 matrix. This is the matrix and this is the 3 cross 1 vector. Then their product would be such type. Multiply first column vector of this matrix with the component of this vector B 5 times 3. Then multiply second column vector of this matrix by -1 and third column vector of this matrix by 0 and add them. Then this would be new vector 11 2. Are you getting? OL. Nice observation is matrices translate from vector inputs to vector output. Here the equation is look like Ax equal to B, where A be m cross n matrices, X be n cross 1 vector. Then our new produces vector would be m cross 1 vector. Here the nice concept, we can create a function from Rn to Rm such that Ax equal to B, where A be the m cross n matrices. Our next goal is span of a vector space. This concept is very important for higher study of not only vector space but also metric space, topology space, for all pure mathematics. Span is actually the set of vector which is actually all possible linear combination of this vector. If we consider span of V1, V2 up to Vp, that means this contains all possible vector which is look like C1 V1 plus C2 V2 up to Cp Vp, where C1 C2 Cp belongs to real number. That means actually span of a set of vector is the set of all vectors which is obtainable by linear combination of original vector. So any set of vector which are non-zero and span of this set of vector means this set contains infinitely many non-zero vectors. For example, if the set contains only one vector V, then this is look like set of those vector which contains A times the vector V, where A belongs to real number. And this is actually the line through the origin. As for example, consider the vector as 1 1. Then this would be this type of line. Consider two vector U and V. Then span of UV would be set of those vector which contains AU plus BV, where AB belongs to real number. And this is actually the plane passing through origin. For example, if we consider V1 equal to 1 0 vector and V2 equal to 0 1 vector, then span of V1 V2 equal to alpha 1 times 1 0 plus alpha 2 times 0 1. This is actually alpha 1 alpha 2. That means by these two vector we can span whole space R2. So span of V1 V2 which contains infinitely many vector, this is the subspace of Rn vector, Euclidean vector Rn. Similarly, if we consider the vector V1 V2 up to Vr which belongs to the Rn, then span of V1 V2 up to Vr is a subspace of Rn. Theorem is let S be subset of a vector space V, then span is always be subspace of the vector space V. That means today I have got one new type of subspace also, span S. And this subspace is the smallest subspace which is containing the set S. This look like, consider S contain the finite element v1, v2, vn. Consider the vector UV belongs to span S and consider U equal to summation I equal to 1 to n lambda I vi and V equal to summation I equal to 1 to n mu I vi. Then there are some U plus V equal to summation I equal to 1 to n lambda I mu I times vi. Obviously, this is also belongs to span S because this is the scalar. So, obviously this is combination of linear combination of vector and Cu would be summation I equal to 1 to n C lambda I times vi. And this is scalar. So, obviously this is belongs to span S. So, by this expression, span S is a subspace of the vector space V and this subspace be the smallest subspace of the vector space V. Here is any subspace containing the element of S also contain the span of S. Now I will stop here. In my next video, I will discuss linearly dependent and independent of a vector space. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.